Hi all, welcome back. So today we are solving two PY questions of instrumentation and process control asked in the chemical engineering GATE exam. So this question is related to GATE 2022. So in other branch like electrical and electronics and instrumentation they do control system basically, but in case of chemical here not pure control system, we have to also add the instrumentation plus process control, because here we are controlling the process, chemical process basically. Okay, so all right, hope this series is going to helpful for understanding the concepts through questions. So this question they given actually like process described by the transfer function. Okay, so we know the transfer function. Transfer function is our Laplace transform of the output, the ratio of Laplace transform of the output to the ratio of Laplace transform of the input, provided all initial condition to 0. Okay, or we can say the Laplace the impulse response, you know, Laplace transform of impulse response. Okay, provided the initial condition 0 or system is relaxed, then we can also define the transfer function. All right, and here this question they given process describe a transfer function. So this transfer function they given. Okay, and here the is forced by a unit step response. So we can say this over the t is equal to 0. You can say this our step response we are giving as input. Okay, you can say this our input. Generally we can consider RT. So t is equal to 0, we are giving the unit step response. So this unit amplitude. All right. The output value immediately after the step input. So after the whenever we give the step input, we need to find out the output immediately. Okay. Where just t is equal to 0 plus, we need to find out the our output, how it's looking to. Okay. So I think and this answer should be rounded up to nearest integer. So nearest integer we need to give the answer. Okay, so hope so. I think in case our Laplace transformation, whenever we deal with the control system, we also walk through and understand the two theorem. One is the initial value theorem. So this question related to the initial value theorem. All right, and second one is a final value theorem. Okay, so if we know the initial value theorem, what's the property of initial value theorem, and how we can, what's the mathematical, how we can utilize this initial value theorem, definitely we can solve this question. All right, so let us first go through the concept overview, then we come back and solve the question. So here you can see concept overview initial value theorem. So limit f tends to 0, t tends to 0, yeah, 0 plus. Okay, and here limit s tends to infinity in case of Laplace domain. This is Laplace transformation. This Laplace domain means S domain we can say. This is a time domain. Okay, if you go more deep, we can say this is like frequency domain, basically complex frequency, right? Anyway, so like in our control system, we have to deal with the Laplace domain. So without converting to a time domain, directly we can find out the our initial value or final value using the this theorem, initial value theorem or final value theorem. All right. So since our given question is related to initial value theorem, so here we have to focus on the initial value theorem. In our coming videos, once final value theorem related question would come, we will explain this one more deep. But still, just we are walking through here final value theorem. So here final value theorem means limit t tends to goes to infinity, then ft, and here is a ft. This is like function, and fs this is like Laplace transform of the this function. Okay, ft. Understood? And multiply s into fs and limit s tends to 0. So what is the purpose of actually this? Predict system behavior at initial and final time without computing full inverse Laplace. Otherwise, what will happen? We can find out the output, and we can put the time in Laplace inverse. Okay, and then put the t equal to 0, t equal to infinity. We can find out. But this is time taking. We only find out the initial nature or final nature, how it look, how it behave. So using this theorem, we can find, we can predict, we can find out actually. Okay, so that's a advantage of this theorems actually. Then before directly we cannot apply this theorem actually. We need to understand the validity and some exception also there. Okay, I mean some special case. Okay, so initial value theorem, wherever we limit we are putting limit tends to infinity, s tends to infinity, that time sfs must exist. Okay, means no impulsive or delta behavior. Delta behavior, impulsive response means that t is equal to 0. We are just giving the very high amplitude, basically here like that. Okay, but impulse response area would be 1 actually. So t this time span is 1 by a actually. Okay, very small time we giving very high or amplitude. Okay, this should not be exist. In case of final value theorem, all poles of SFS. I am not talking about simple only capital Fs. I am talking about S into Fs. All should be in the must in the left half the S plane. System must be stable. Okay, means I am focus on system should be stable. Then only final value theorem. If you apply, you will get the correct answer. Otherwise, you will end up some wrong answer. That time final value theorem would not be applicable. All right. So for example, like fs is for example uh, let us say s minus 2. Okay, and if you are applying the final theorem, just I am giving the hint here, 0. So s into fs is given s minus 2. If apply, you will get 0 answer, but this answer wrong because here system is unstable. So final value theorem will not applicable, get the infinite, because this is unstable, right? System is going to diverge, so final value theorem will not settle. All right, got my point. So that's the things we need to take care actually. And in case of oscillatory system, like if you get sine cos kind of thing, oscillatory system, that time final value will theorem will not be determined actually. So either system unstable or it is oscillating, we cannot find out the final value theorem. We cannot find out final value using the applying the final value theorem. All right. Okay. So one more thing actually, like I'm just discussing a final value theorem little bit. S into fs, like let us say fs is here s minus 2, for example. So here s is cancel out, but still be getting the sy 1 by 2, you will get minus 1 by 2, but this answer will not be exist. If you apply final value theorem, you will get minus 1 by 2, but practically, I mean real sense, this will not be applied because this is a 1 by s minus 2 means pole is right hand side, system is unstable, so we will not settle. We get very high value, I mean infinite. So real we get high value means infinite. Yeah, final value theorem will not applicable. Okay, this value wrong. So that's a very important in final value theorem. Okay, anyway, in future once we got this related questions, we will explain more detail. Come back to initial value theorem. So in case of final value theorem, let us say here they are saying poles are right of the explained. I already explained, and poles are origin. Okay, you can see here. Okay, it cancel out. Okay. So here in case of limit s tends to infinity, yes, fs is exist. It should be exist actually. How we can say? I am talking about right now initial value theorem. Shortcut I am putting here initial value theorem. Full form initial value theorem actually. So this we must exist and be finite. We want this value should be finite. Okay. So it means in time domain function ft, our real function is always in function right time. Okay. But in case of our simplifying and solving all things in control system, we using the Laplace domain. Okay. So fd must have the finite value at t is equal to 0 plus no impulse delta t or derivative present at a t is equal to 0. Alright. So that's so important. Okay. So here you can see if you why impulse break initial theorem, because ft is equal to delta t, then fs is equal to 1. Laplace domain of the delta t is 1, right? So s into fs equal to s, we will get infinite value. Got my point? Yeah, we can say this is not exist. So this I put some examples here. You can see initial value theorem, you will get here 0. Final value theorem, you will get here 5 by 2, because this is correct only because this is stable. All poles as a left of the S plane, then okay, we get 5 by 2. But here if you get here this question was like that, then you get 5 by minus 5 by 2 in if you apply the final value theorem here. But this question, this answer wrong, because the system is unstable, we cannot apply final value theorem. Otherwise we can say it go to response going to diverge, so our answer would be infinite. Yeah, final value theorem would not applicable. So let us focus on significance of these theorems in control system perspective. All right. So estimate initial and steady state values. Initial value, apply the initial value theorem. Steady state values, apply the final value theorem of the system outputs. Check stability, performance, and settling trends. Sorry. Validate steady state error with final value theorem. Okay. So in case of steady state error, we apply the final value theorem. So useful in a PID design, controller design, not PID only, we can choose other controller also, and root locus evaluation. Okay, we'll discuss these things. Okay, so hope you have to understand the fundamental of the initial theorem. Now I think this question very simple. They are saying our output, right? What is the output? We can find out here. Output, let us say for example by s, our input is rs and transfer function is GPS. Okay, So what is the RS actually here? This is a step input. So Laplace transform of this statement 1 by s into GPS. GPS is already they given 10s plus 1 by, okay. So our output is 1 by s into like that. All right. So here we want to apply here initial value theorem. So t tends to 0, yeah 0 plus. So here is a by p. I am putting in time domain small by p. Okay. We can no need to solve in inverse Laplace. We can directly manage in Laplace domain only. So here no need to solve Laplace inverse basically. Okay. So here we applying this our initial value theorem. Will fulfills our all condition. There is no like impulse response, so we can directly apply here. So before apply this theorem, first we have to check actually. Okay. Sorry. Yes, this is 1 by s right here. So s is cancel out here. So now we can also write like that s infinity. So just take s common here to 10 by 1 by s by s. Similarly, we can do here also. Now if you apply the infinity here, so 1 by s going to 0. So we'll get 10 by 5, we'll get answer 2. Alright. So our answer of output of the initial iteration will be like that. If you apply the input unit response, so our output will start from the just t0 plus, you will get some value 2. After we don't know whether going to like just some erase some value, yeah, coming down like that. For this we require the our inverse uh, this final value theorem actually. Let us say apply what is the final value theorem here. If you apply final value theorem, then t tends to infinity. For given question, answer gets solved. Okay, so answer would be 2. I am extending our question here. So limit s tends to 0 s by s. Okay, so what will be the answer actually here? S 1 by s 10s plus 1 by 5s plus 1. So s cancel out and 0 if you take it 1 by 1 actually. So basically t tends to infinity, t tends to 0. So it is equal to 0. That time it start from 2, and whenever it reaches t infinity means very, so it will be like that 1 actually. Whatever our input there na, our input is 1 actually, right? So it will be reach this in reference input, because we are giving force input is, our input is 1, so it will reach the input actually. Okay, reference input. Okay, we start from 2. Okay. I do one more thing actually. Let us do the Laplace inverse. So by ps is equal to 1 by s, but initial and final theorem we can get some idea, prediction of the behavior. Because if you don't know final value theorem here, we cannot tell whether we know that t is equal to 0, this value is 2. Okay, and then how is behaving diverge, yeah, going to converge actually, right? Okay. So 1 by s, 10s plus 1 by 5s plus 1. So I'm just doing the what we can do actually here, we doing the some partial fraction here. Okay, so what we can do actually partial fraction here, so this should be equal to same this one, right? 1 by s, 10s plus 1 by, okay. So plus b into s equal to, numerator can cancel, you get this one. Then just we just collect the same term, you will get 10s plus 1. Just compare it. So here a plus b equal to 10 and a equal to 1. You just check it. So a is 1, then b get the our 9. A is 1. Alright. I think we commit mistake, right? This should be a 5a. Okay, 5a. So here whenever this 5a, okay, I think now it's clear, right? 5as now. Let me check once. 5as plus 1a, so 5a plus as there na, so 5a plus b and a, okay, all right, I think. So here our a is 1, so b is get the 5 and a also get the 5, all right. So you will get like that, 5 by s plus 5 by 5s plus 1, right? So you can also write 5 by s, you can take 5 common here, so we will get s plus 1 by 5, right? There is no problem. So now you are in position, you also take like that, 5 cancel out, so s plus 1 by 5. So here you will get 5 if you take Laplace inverse here, our input in, sorry, output in time domain, you will get 5 by 1 minus e the power t by tau. Sorry, this is our 1 by 5, right? Okay, you can say like that. Okay, I think we correct na, 10s by 1, 5s by 1, right? Okay, let me check once actually. 10s plus 1 by 5s plus 1, so 5s plus 1, it looks correct, right? 5a plus b equal to 10, a is equal to 1. Oh, I commit mistake, right? Here a is 1, right? Not the 5, this one na. So that's why let us correct it, no problem. So one thing you understood that here a chance to calculation error actually, right? So this is a, so here is a, don't put here, this is a 1, this is our 5 and this is okay, and not here 1 and 5 cancel out, this is okay, right? So here is a 1 actually, so our answer would be 1 into e the power minus t by 5. Now if you try to find out initial value theorem or final value theorem, you can find out immediately, right? Because we know the time domain. So initial theorem actually means just put the infinity here. Okay, so this will be going to 0. Again, I think a commit mistake. Huh? Let us check actually. This is a 1, so 5. It will be 5, right? A V 5. Okay, so now it's okay, right? Okay, no problem. So here, if you apply the final theorem here in time domain, then it will be time domain. It means final wave theorem, right? So it will be t tends to infinity, right? So what is actually answer? 1 minus 1 infinity minus infinity will be 0, right? So we'll get one answer actually. But if you apply the initial value theorem, then t tends to 0, right? Actually here this is a positive here, right? You can see a plus. So answer here plus. Okay. So not minus, here is a plus actually. Okay. Because I am bothered about the initial value theorem, the answer should be 2 actually, but not coming. Now it's coming. So here is a 1. No need to write 1 actually here. So 1 plus, if you apply t tends to 0, then e the power minus 0, you will get 1, 1 plus 1, you will get 2. Now it's okay, right? So we have verified in time domain also. Okay. So one thing there, in case of this theorem, in our time domain we'll get the correct answer, but it will be taking time because we need to solve inverse Laplace. Okay, time taking, but based on time, if you have a doubt, you can make sure, okay, you can solve, no problem. So that's all. Already I think it's going long video. So that's all. I hope you understood this question. So for given question, answer would be 2. So we have verified with the solving the time domain also, and we also verified in the initial value theorem concept. Okay, so that's all.